A2 Further Maths, second order differential equations. Okay, so before we move on to the next part of differential equations, what I'd like you to do, please, is just grab your notebooks out, because we are just going to look over some other sort of key language that we need to understand and use later on. Okay, so the key language we're looking at is the word homogeneous. So if every term of a differential equation contains the dependent variable, it's called a homogeneous differential equation. I'll show you an example of that. It makes more sense from an example. So an example that we could use is one like this. So we can see that the dependent variable there is the y value. Remember that the number on the denominator is the independent variable. So y value is the dependent variable. So we can see this is to do with y here. Okay, this is to do with y here, and this has got a y here. So it's definitely a homogeneous equation because it's got the dependent variable in every single one of its terms. An example of something that's not homogeneous though, okay, so an example of something that's not homogeneous would be, to make it simple, putting it equal to 7. So this isn't homogeneous because you've got the y term there, good, the y term there, which is the dependent variable there, the y value here, but there's no y's on this side, so therefore it is not homogeneous. Okay, so just pause there, get down what you need, all right, and make sure you understand what that word means, because we are going to be using it later on. Okay, so just pause if you still want more time. Okay, so we've spent some time looking at first order differential equations, but what we're going to move on to is what we call second order differential equations. And the reason why they're called second order differential equations is because it's got the second derivative in there. Now the ones we're looking at here at the moment is called the second order homogeneous differential equation, because as you can see, each of the terms has got a y value in it. Obviously 0 does not count, okay? Argue that 0 times y is still 0. So there's y value in there in each of these three parts. So this is what we can call a second order, because its highest order is the second derivative. And it's homogeneous because you've got the y dependent variable in every part of it. What I'd like you to do is I'd like you to transfer that equation by using the substitution y equals e to the kx. So I know it's for your notebooks, so I want you to get that down. I want you to pause it, grab a scrap paper, grab your whiteboards, whatever you like, and just try using that as your substitution. So think about what y equals, what dy over dx would equal, what would d squared y over dx squared equal, and then substitute them in and see what you get. Okay, right, let's have a look what you got then. So hopefully you started with y equals e to the kx. Okay, because I told you that's your starting position. You've differentiated that and you've got k e to the kx. And while you're doing it, you may as well differentiate a second time then, because you'll need that, k squared e to the kx. So for that one substitution, y equals e to the kx, I've managed to work out the first derivative and the second derivative. What I'm going to do now is I'm going to substitute those back into this equation. And if I substitute them back in, I get this equation just here. And what's important about this equation is that e to the kx, the exponential function, and the exponential function here and the exponential function here are all in common. So I could definitely factorise those out. And so then I've got a to the k squared plus bk plus c equaling 0. And because I can factorise out that e to the kx, and most importantly, because it's an exponential function, it's great how it differentiates, but also it's great that it can't equal 0. We know an exponential function can't equal 0. So therefore, if e to the kx is cancelled out because it can't equal 0, the ak squared plus bk plus c must equal 0. And you look at that now and you think, well, that's just a basic quadratic equation. And it most certainly is. You've got a quadratic equation just there. We need to consider what the k value is. We're going to come back to that later. All right, we can see that the k value is going to come from this. But most importantly, a second order differential equation can be boiled down to this quadratic equation just here. Okay, so get that bit down in your notes. That equation is really, really important. and it's so important it has its own name. It's called the auxiliary equation. So the equation AK squared, this one just here, plus BK plus C equals 0, is called the auxiliary equation of a second order differential equation. Okay, just get used to different language. Sometimes I put down different notation on purpose. So this equation here and this equation here are identical. So by all means, put a big arrow between those two to say, look, these two are the same things. Okay, exactly the same things. It's just slightly different notation. Y double dash is second derivative of y. Y single dash is the first derivative of y. And of course, there's no y values just in there. On this side equals 0 plus cy on that part. Okay, so take your time, get down what you need. Okay, so what I'd like you to do is, now you know what the auxiliary equation is, see if you can work out the auxiliary equation for those three examples just there, those three differential equations. See if you can work out the k values for each of them. And then if you can work out the k values, then what you can do is you can then work out the solution for y in terms of x. So see if you can do that for each of those three best you can. All right, pause there. Just press play when you're ready and we'll have a look through them. Okay, so let's have a quick look at the first one then. So hopefully, yes, you can use the full substitution every time, but you don't need to. You could write this straight away as k squared minus 5k minus 6 equals 0. All right, so you can get down to that equation straight away, but you're always using the same substitution. Y equals e to the kx. This is always identical. All right, so that's important. That will help us in a minute to get our answer. So because we've got this one, you can use your whichever means you like to get your quadratic equation solution. So you can solve it. In this case, we get 6 and minus 1. All right, I'm sure you've got your calculators to do that for you. So once we've got those two values, that's going to give us, well, the problem is it gives us two solutions. It gives us y equals e to the 6x and y equals e to the minus x as our two solutions to this equation. And if we substitute either of those in, try it yourself. E to the 6x, y equals e to 6x. So substitute it in there, differentiate, substitute in there, differentiate it next time, substitute it in there. And just convince yourself that when you do that, all the numbers cancel out and get you 0. Okay, so just do that now. Pause, have a go at substituting in e to the 6x. Try the same for e to the minus x. And that one's a bit easy to see. We can see that we get minus 6 e to the minus x minus 5. So plus 5 e to the minus x. And it goes back to plus again. So this one's just going to be e to the minus x. So therefore you're going to get 1 plus 5 minus 6 equals 0. So it definitely works for minus 1x. Okay, again, just pause though and write it down. Make sure you're happy that it does work. So if we've got two sets of solutions though, what can we do? Well, because we've got two sets of solutions and we know that when we differentiate, you just differentiate each bit individually, you can combine those two solutions together to get a general solution, which is going to be a e to the 6x plus be to the minus x. So you can actually combine those two solutions together and therefore give you what we call a general solution. And notice that you've got these coefficients a and b on the front. Again, just convince yourself you're happy that if you had an a value on the front of each of these, it wouldn't make any difference. It would still cancel out and get you 0. All right, so just check that and make sure you're happy that a number on the front, this extra constant, doesn't make any difference. Okay, get your general solution. Okay, so pause there, take down whatever you needed. All right, so let's have a look at the second one then and just see what you did for the second one. So hopefully you noticed in this case that we had two solutions, but they were repeated. So k squared minus 4k plus 4 gets you k equals 2. Now, the problem is, and should have maybe mentioned it in the previous one, when you've got a second order differential equation, the solutions to a second order differential equation should have two, if it's a general solution, should have two unknowns because you've integrated it twice. So you should have two unknowns in there. Now, if you've got two unknowns, Last time it was fine because you had two clear roots. So you had a clear A and a B. Whereas in this one, you can't do that. You're going to have a e to the 2x plus b e to the 2x combines to make a plus b, which is just another constant. So there is a problem. Okay, there is a problem with this one. So the only possible solution is a e to the 2x. But we've seen this hint before, that when we had a particular integral in a previous lesson that was very similar to the form of the general solution, we could do something. And you could do the same trick with this. Because we've got two equations which are pretty much the same, e to the 2x, we can manipulate the second one by having it as x e to the 2x. So multiplying this extra factor of x in there means you can write a second function. So we've seen that trick come up twice now. This idea that if we've got a repeated one that's too similar to the same form, then we can put in this extra factor of x. Why does that help me? Because now, because I've got a repeated root, I've still got two of them. I've still got two constants because it's a second order differential equation. If it's a first order, you have one unknown. Second order, you get two unknowns, and so on. The pattern carries on. I can now combine these two and get y equals bx, just proving it to you, just showing that it's actually true. Okay, so there's the second derivative. There's the first derivative. Noticing that you need to be careful with this 2bx e to the 2x. Right, because you're going to have two lots of it, so that's where that bit comes from. What happens next? You can substitute these back into here. So d squared minus 4 dy over dx. When you substitute them in, we get 4 lots of that, 4 lots of, minus 4 lots of this, plus 4 lots of this one, and you'll notice that they start to cancel out. So the 4b squared cancels with that minus 4bx squared. That 4bx squared there is going to cancel with, will be combined with this one here. Okay, so that's 8bx squared, but you've got minus 4 times 2, which is minus 8 bx e to the 2x. So they all cancel out, leaving you 0. So it's definitely a solution. Just showing it there, proving that that actually works. Great, yes, equals 0. Right, so because that's a solution, and because that one's a solution, I can then write the general solution out for this then. And so the general solution is going to be y equals a e to the 2x plus bx e to the 2x. And of course you can factorise out that e to the 2x and just have a plus bx. So this is important. When it was two unique values, two roots, right, two unique values, then it was fine just to write it as e to the first value plus e to the second value with an a and a b at the front. If it's a repeated root though, okay, if the discriminant came out as 0 and it's a repeated root, then we have to write it as a plus bx e to whatever that repeated root is, x. Right, so there's no surprises on the last one then. So you've got the last one, and you would have noticed that this time we have a bit of an issue because when we tried to find the solutions, of course the solutions are not real. Now you guys can handle that, so you can still write down the two, in this case, the two complex roots. So we've still got 3 plus 2i and 3 minus 2i as our two roots of this quadratic equation. Does that mean I can still find my general solution? Yes, it is. You can find general solutions because that's those two. Noticing that you've got an a and a b as my two constants because it's a second order. So there's my two possible answers just there. Not very neat though, and I don't like the fact I've got some complex numbers in there. So is there another way of changing this? Okay, so I've got my general solution just there. But there is ways of changing it, isn't there? We've seen it before. We've seen how to change exponential form into other forms of complex numbers. So I could write this. I could certainly pull out the e to the 3. So I'll use my laws of indices like it says there. I can write e to the 3x plus 2ix can be written as e to the 3x, e to the 2ix. So I've separated out using my laws of indices. Same with this one. Okay, I haven't divided it. I wanted to keep it completely separate like that. So there we go, I've done that part. And what I can also do is factorise out that e to the 3x then. And if I factorise out the e to the 3x, I've got ae to the 2ix plus b e to the minus 2ix. Now that's quite important, this rule just here, because we have definitely seen this before. We've definitely seen that we can write the e to the ni, so to speak, and same with this one, minus I, in the form of cos x and sin x. And that's exactly what I'm going to do now. I know that e to the ix is this, so if I substitute that in, right, and replace the 2, which is clearly going to go at the front of them both, and then this part just here, then I get this. So convince yourself you're happy. So this bit here, because it's like the 2x, I2x, that's where the 2x comes from. The I goes on to the front of this bit. The A just stays at the front of both of those. This is exactly the same, but it's minus 2x, so I'm just putting the minus in there and there. Can I neaten this up any more? Well, I know for a fact that cos minus 2x is the same as cos 2x. And I also know the fact that sine of minus 2x is the same as minus bi sine 2x, because I know about the cos of a negative and sine of a negative. So I can definitely sort those two out. Seen that so many times now, I feel that you should have been able to do that without any problems. So this one goes to minus. I can just factorise a little bit, can't I? Because I can see these two have got I sine 2x in common, and these two have got cos 2x and cos 2x in common. So really, I could write it like that. Again, just pausing, making sure you're happy. So if that's the case, then I can see that really a plus b is just another constant, isn't it? A is a constant, b is a constant. So a plus b is just another constant. That is just a number. And the same here, a minus b, even I is just a number. It's the square root of minus 1. So a plus b, a minus b is still a constant, times by I is still a constant. So what I can do with these two constants is just replace them with another letter. And I can replace them, let's just go with the next letters down, C and D. So really, I could write this as y equals e to the 3x, c cos 2x plus b sine 2x. And what I'd like to do is just have a bit of pattern spotting. Have a look at that as your final answer to this one. And have a look at that as your solutions and your roots. And just see if you can spot any patterns between the answer you got out in complex form and the final answer as the general solution with its two unknowns. Right, well done if you spotted that the 3, which is in front of both of them, went there, and the 2, it didn't matter whether it's plus or minus, just the positive 2 went in there. Now it's a bit of guesswork. All right, it's just guesswork because you can just see it on this one pattern, but it is always true. Okay, so just like you grab your notebooks then, please. Let's just take down some notes of what we found out from those 3 examples and just formalise it. So we're looking at the auxiliary equation. So we're looking at a situation where we've got differential equation, our second order homogeneous differential equation, and we found the auxiliary equation and we found it to be of this form: ax squared plus bx plus c equals 0. Okay, so we've got that situation just there. Now the equation we can get, the general solution to this differential equation then, can be found by investigating the discriminant. The discriminant of this quadratic just here dictates what the form of the general solution for y is going to be. And the discriminant can be 3 different values, of course. Now if we've got it as a positive number, so if the discriminant comes out as a positive number, which we saw first of all, then the general solution looks like this: y equals ae to alpha being the first root plus be to beta x, where beta is the second root. So just make a note of that in your notebook. That is the general form if it comes out as 2 distinct real roots. Now you could actually show it all from scratch by setting y equals e to the kx and substituting it all in, but you don't have to. You can learn that general form yourself. Okay, so that's the first one. So the second one is if the discriminant equals 0. Now, if the discriminant equals 0, then the form looks like this. Y equals e to the alpha x, lots of a plus bx. You've still got two general parts there, the unknown parts, because it's a second order differential equation. So you need these two. Always got two unknowns, all right, two constants. Whereas because there's only a single repeated root, there's only a single alpha value in there. So whatever your repeated root is, you put it in there, and then in brackets a plus bx. Okay, so that's what happens if it equals 0. If it's less than 0, okay, in other words, you have complex roots, then what's going to happen is you can rewrite it in this form. So this is the most complicated one. So y equals e to the px, a cos qx plus b sine qx. And these two are exactly the same, and the a and the b value are your constants. In this case, b will be a complex conjugate constant, but it's still constant values. You've still got two of them because it's still a second order differential equation. Now the p and the q parts come from the complex number itself. So if you figured out the complex root, the real part to it goes as the power of the exponential, and the imaginary part of it, the q part, is the part in front of the cos, the x on the cos and the sine. So if you know what your complex root is, and of course, because the a, b, and the c are going to be real, it's always going to be p plus or minus qi, all right, because a, b, and c are always real, then what you're going to have is, as long as you remember which way around it goes, p would be your power there, and q would be your value for your angle, just that you put in those two. Okay, so pause there. Make sure you've got plenty of time to take down what you need. Okay, so let's have a quick look at a question then. I would like the general solution of the differential equation 9 d squared y equals 4y, but I also want the particular solution as well in this situation. Okay, so what you could do is you could actually have a go yourself, got your notes in front of you, or you might want to wait and we'll go through it together. Okay, so let's see what you got then. So I'm going to write it in the form like this. So just putting everything to one side and making it equal to 0. So that helps me find the auxiliary equation. So because I can write it equal to 0 like that, notice there's no dy over dx term. That's okay, we'll deal with that. Okay, it's interesting they're giving us a dy over dx term there. So there's no dy over dx term, that doesn't matter. So we've got this part just here. I know the homogeneous equation is going to be 9k squared minus 4 equals 0, where y equals e to the kx. So I just get used to writing that down. Sometimes I get used to writing it down because if you ever forget, you can actually substitute it back in the values and write your answer that way. So I've got that as my substitution. So there's my auxiliary equation. Bit of rearranging. I can see I'm going to get 4 over 9, which is the same as 2/3. But we notice that the two individual roots are either plus 2/3 or minus 2/3. So the discriminant, just to check, comes out as a positive. So therefore, because it's positive, your general solution is going to be in the form y equals a e to the alpha x plus b e to the beta x. So it's nice with the two distinct roots. So I can take my two distinct roots, I can substitute them into that formula, and therefore I've got my answer. Or you could just do it all manually again yourself by substituting it there and then substituting it in. It doesn't really matter. Okay, just this way is a bit quicker. So there we go. I've got the general solution, tick. I haven't got the particular solution just yet. So I need to keep an eye on that general solution and make sure I've written that down. Just pause if you need more time. So there's my general solution. So my two particular solutions, one of them says when y equals 6, x equals 0. So I've got x equals 0, that's going to cancel that out, and that cancels out. Gets me 6 equals a plus b. Not very helpful though. Okay, so that bit on its own is not very helpful because you're just going to get 6 equals a plus b. I also need to use this. But to use this, I need dy over dx. Okay, it's got nothing to do with the fact it didn't appear in there. I know what y equals now. in its general form. So what I can do is I can definitely work out dy over dx. So I've got that first one, yes, 6 equals a plus b, not very helpful on its own. The second differentiating though is very easy. It's just bring the 2/3 to the front, bring the minus 2/3 to the front there. So I've got that. And now when x equals 0, this is going to go to 1. This is going to go to, sorry, go to 0. That's going to go, excuse me, right the first time. That's going to go to 1. That's going to go to 1, leaving me 0 equals 2/3 a minus 2/3 b. Okay, let's go through it. There we go. Right. Now, of course, if it's 2/3 a minus 2/3 b, that's the same as 0 equals 2a minus 2b, or 0 equals a minus b. Now I've got these two equations. You can solve them simultaneously. You can see just add them together, gets you your a value, take one away from the other to get your b value. And so I get a equals 3 and b equals 3. That's my two solutions. So now I've got a particular solution to this equation, to this differential equation just here. My general solution, my particular solution, sorry, is going to be when those two equal 3. So therefore it is that. And you could check this yourself. If you differentiate that twice and times it by 9, then what you'll find is you get exactly the same answer as if you had 4 lots of this original equation. So just try it and convince yourself. Make sure you're happy. Differentiate that twice to get d squared y over dx squared. Times the answer by 9, and then go back and times this answer by 4, so you're going to get 12e to the 2/3. Did your answer come out as 12e to the 2/3 for that way? It should have done. You should have got a solution to that. Okay, so what I'd like you to do is just have a go at completing the exercise on 11C and see if you can solve the equations using the homogeneous second order differential equations. Okay, so what happens if it's not a homogeneous equation? What happens if we get a situation like the one in front of us that's clearly not homogeneous because we got y, y and y as our dependent variables there and no y's at all on this. Now the way we're going to solve it is by first of all making sure it's rearranged so that it goes as an equation that's got all the y terms on this side equals all the x values on this side. Okay, all the bits that are not in the homogeneous equation. Okay, and the reason why we can do that is then when we look at the complementary function, this side is going to equal 0, and this side here would then be homogeneous, and we can start to find our general solution. Okay, so I'm just going to pause, give you a chance just to do that. You might want to have a go yourself now, giving you that hint of finding the complementary function and the particular integral. You might be able to do it all yourself, but by all means, either have a go or just listen to my solution. Okay, so what we're going to do is we're going to just, given that we're going to check the particular integral first of all. Okay, we're going to start with this bit. So check this is a particular integral of that differential equation. It's highly unlikely that the general solution of this is going to be of the same form, so it's okay to check this bit straight away. So we get 3 minus 2x is when you differentiate the first time, and then of course that's going to go to minus 4 cos 2x when you've differentiated it the second time. And once we've differentiated both of those, we can substitute them in, and hopefully we're going to get to 12x plus 12 minus 8 sine 2x. And lo and behold, when I substitute it in, so I've substituted that part into there, that part into 4 lots of it, that part into 4 lots of y. There you go, so I've substituted it all in, and out comes that, which simplifies to exactly what we want. So I've done the first bit. I've shown that that is a particular integral to this differential equation. Okay, so I've done the first part just by substituting there. I've shown that that definitely works. That is a particular integral. What I want to do now is find the general solution of that differential equation. So I might have the particular integral, but I also need the complementary function as well. So I've got to find that out. Okay, so just pause if you need more time. Okay, so we're going to find the complementary function then. And we can find the complementary function exactly the same as we did with first order differential equations by setting it equal to 0. And then the moment we set it equal to 0, we've got a second order homogeneous equation to solve. So we can use the same technique that we just done, or you just practiced with that previous exercise. If we've got that, we can look at the discriminant, we can work out what our general solution is going to look like. We then need to think about adding the particular integral, but let's just go with this bit first. So we've got, what's the auxiliary equation? That's when y equals e to the kx. Solve it using whatever technique you want. In this case, k is going to equal -2, and it's a repeated answer. So that means that we're going to have y equals e to the -2x a plus bx. So that is my solution. Okay, so that's my solution. Or so yeah, my general solution for this homogeneous equation. So how do I get the general solution for the whole thing? Well, I've got the general solution to that part, which is e to the -2x a plus bx, but that would get me 0. So how do I get this bit? Well, I need the particular integral. And so that's why the particular integral is added on to the complementary function. This part just gets you 0 when we differentiated it once and then twice and put it into there, but this part gets the bit I want. So well done if you followed that. Pause there to give you enough time to get down what you need, and then when you're sorted, you can move on. Okay, so having a go at this exercise 11D then, and that's solving non-homogeneous second order differential equations.